Welcome to RootResearch, where we decode science in plain language and connect it to the bigger picture of how we understand reality. Today, we're stepping into one of the most important moments in human thinking, the realization that the universe itself is not standing still. This insight was written down almost 100 years ago by Edwin Hubble, working with observations from Mount Wilson Observatory, together with collaborators like Milton Humason. Let's start. What if I told you the universe is doing something right now, even as you listen? Imagine standing on a sidewalk watching cars drive away. The farther the car, the faster it seems to disappear into the distance. Now imagine realizing that every car in every direction is doing that at the same time. That moment of realization is what this story is about. Why should you care? Because this idea quietly changed everything. How we think about space, time, beginnings, endings, and even our own place in the universe. Before this work, the universe was often imagined as eternal, static, and unchanging. After it, the universe became dynamic, expanding, and alive with motion. This was not philosophy. This was measurement, and it started with light. How do you even measure the movement of something that far away? Hubble didn't begin with a grand theory. He began with a practical problem. Astronomers had already measured something strange. Many distant nebulae, and what we now call galaxies, showed light that was shifted toward the red end of the spectrum. Redshift, in simple terms, is like hearing the pitch of a siren drop as an ambulance drives away from you. Light behaves the same way. If a galaxy is moving away, its light stretches, shifting toward red. The faster it moves away, the more stretched the light becomes. The hard part wasn't measuring the redshift. That part was already being done. The hard part was answering a deeper question. Does the speed at which a galaxy moves away depend on how far away it is? To answer that, Hubble needed distances, real distances, not guesses. Measuring distance in space is like measuring a city from a mountain. Hubble relied on something clever and very human: comparison. Some stars behave in a predictable way. Cepheid variable stars, for example, brighten and dim on a regular schedule. If you know how bright they really are, you can compare that to how bright they look, and from that difference, calculate distance. It's like seeing a street lamp at night. If you know how bright street lamps usually are, you can tell whether it's nearby or far away just by how dim it appears. Hubble and his collaborators used these stellar standard candles to estimate distances to nearby galaxies. For farther ones where individual stars were harder to see, they used statistical brightness, comparing whole galaxies instead of individual stars. It wasn't perfect. Hubble knew that. He openly discussed uncertainties, errors, and limitations, but the data were good enough to test one idea, and that idea was simple. What happens when you line up distance on one side and speed on the other? When Hubble plotted galaxy distance against radial velocity, how fast a galaxy was moving away, something remarkable appeared. The points didn't scatter randomly. They lined up, not perfectly, not cleanly, but clearly enough to see a pattern. The farther a galaxy was, the faster it was moving away. This wasn't just true for one or two objects. It showed up again and again across the data he trusted most. In plain language, distance and speed were linked. This relationship is now famous, but at the time it was quietly revolutionary. Hubble described it cautiously, even conservatively, but the implication was unavoidable. Space itself appeared to be expanding. This conclusion is documented directly in the original paper. Why this was shocking to scientists at the time? Up until then, many scientists assumed the universe was static. If galaxies were moving, maybe they were just drifting randomly. Maybe the Milky Way was moving through a fixed cosmic background. Hubble tested that idea too. He corrected for the motion of our own sun and galaxy. He checked whether the observed velocities could be explained by local motion alone. They couldn't. Even after corrections, the velocity-distance relationship remained. This suggested something much bigger was happening. Not galaxies moving through space, but space itself stretching. Think of dots drawn on a balloon. As the balloon inflates, every dot moves away from every other dot. No dot is special, no center is required. That mental image still helps students today. A universe with a memory of time. One of the quiet but powerful ideas hinted at in the paper is this. If the universe is expanding now, it must have been smaller before. Hubble did not aggressively push this conclusion. In fact, he explicitly said it was premature to discuss all consequences. That restraint is part of why this paper still commands respect. But the door was open. If expansion has a rate and distances increase over time, then time itself becomes part of cosmic structure. The universe gains a history. This is where later ideas like the Big Bang would eventually grow. Not from philosophy, but from measured numbers. Why the data were messy, and why that mattered, Hubble emphasized that galaxies don't move perfectly with the expansion. They also have their own local motions, like cars weaving slightly as they all head down a highway. These peculiar velocities added noise to the data. Some galaxies moved slower or faster than expected. Some even appeared to move slightly toward us. Instead of hiding this, Hubble highlighted it. He showed that when you average over many galaxies, the pattern becomes clearer. This was an early lesson in statistical thinking applied to the cosmos. Real systems are messy. Patterns emerge anyway. A hypothetical situation you already understand. Imagine you're inside a rising elevator with friends. Everyone is walking around randomly. Some toward the door, some toward the wall. If you only watch one person, it's confusing. But if you step back and notice that the floor number is increasing steadily, you realize something important. No matter what people are doing locally, the whole elevator is moving upward. That's what Hubble saw. Galaxies wander locally. Space expands globally. Both can be true at the same time. Why this still matters in real life today? You might wonder, this is cool, but how does it affect me? Here's one answer. Every GPS signal, every satellite orbit calculation, every cosmological model depends on understanding how space and time behave. The math behind expansion feeds directly into how we calculate distances across the universe and how we test new physics. Modern discoveries like dark energy, cosmic background radiation, and large-scale structure tracing all rest on this foundation. If this early relationship had been wrong, much of modern cosmology would collapse with it. Instead, it has survived nearly a century of increasingly precise measurement. The courage to say, "This looks real." One of the most human moments in the paper comes near the end. Hubble admits uncertainty. He acknowledges that future data might refine or even modify the conclusion, but he also states plainly that the relationship is evident and dominant in the data. That balance, humility with clarity, is rare. He didn't overclaim, he didn't understate. He let the evidence speak. So, what was the main outcome? Here it is, said simply. Galaxies are moving away from us, and the farther away they are, the faster they move. This implies that the universe is expanding. Not metaphorically, not symbolically. Physically. Space itself stretches. That single idea reshaped science, philosophy, and humanity's sense of origin. Take a second. The atoms in your body were forged in stars. Those stars formed in galaxies. Those galaxies are writing the expansion of space itself. You are not standing still in the universe. You are moving with it. A quiet thank you to Edwin Hubble and the scientists who followed the data wherever it led. If you like what we do here at RootResearch, subscribe, share your thoughts in the comments, and tell us which piece of science you want decoded next.